Hello everyone, and welcome to the first CosKASI ECR seminar of this year. It's a great pleasure for me to introduce our speaker, Alba Kalaja. And Alba did her master's at the University of Padova and is currently doing her PhD at the Van Swinderen Institute in the University of Groningen. Sorry about butchering that. With Dan Meerberg. Today she will share her research on the reconstructed CMB lensing bispectrum. So Alba, please start when you're ready.
Yeah, thank you so much. It's really a pleasure for me to give a talk here, and thank you for giving me the opportunity and for also the opportunity to virtually meet you all. It's really great. So yeah, today I'm going to talk about a work on the CMB lensing bispectrum done with my supervisor here in Groningen, Dan, and Giorgio, and then some other people from Cambridge and from Tokyo. So we had kind of a more international collaboration, and yeah, very funny Zoom call times. So let me start. So yeah, I just want to mention that some part of my work was also done at the Flatiron Institute, and I'm also part of the Simons Observatory. So you maybe hear this during the talk. Okay. So I will start, obviously. So first of all, the focus of the talk will be on mostly the challenges that we will encounter in measuring the lensing bispectrum, and in particular, the reconstruction noise biases. But I will obviously give an introduction to get everybody on the same page. And then I will explain why we go beyond the Gaussian assumption and we look at the bispectrum. And I will give an overview, brief one, about the lensing reconstruction from CMB and isotropies. And then I will go to the core robot work and show some analytical results and simulations, and in particular of how we use FEYNMAN diagrams for lensing. And I will give my conclusions. So let's start from the introduction. So the photons of the CMB, after they're emitted, they travel freely through the universe. They encounter the large-scale structure of the universe, so the distribution of matter, and then the photon's path is deflected by the inhomogeneities in the matter distribution. This effect is can be seen in the observed CMB anisotropies. Here you see a patch of the sky of the CMB that is being lensed. So you probably have a hard time seeing the effect, but that's the point of it. The effect of lensing is really small and it's coherent across several degrees. But it's still a signal that can be measured and can be used to do some cosmology, an interesting cosmology. Getting to the details, what happens effectively is that temperature anisotropies of the CMB get remapped, so their position gets remapped by deflection angle, which is given in terms of the gradient of a certain quantity that we call the lensing potential, which is in turn defined as the integral of the gravitational potential psi across the line of sight, where chi is the co-moving distance. And as you can see, this integral goes from chi star, which in this case is the recombination, the distance to recombination, up to now to 0. And so as such, the lensing potential traces the structure of matter across several redshifts. And so it can give us very interesting information about the growth of large-scale structure independently of large-scale structure service. So this information comes from the CMB. And on neutrino, they can be used to determine neutrino mass hierarchy and also dark energy models, especially when you look at redshift closer to us, where the effect is more important. Now, if you, as I showed you, this angle here is very small, and so what we can do is to expand this expression here and expand this in the gradients of the, in terms of this angle, which is the gradient of the lensing potential. And as you can see also, this expansion depends also on the gradient of the temperature anisotropies. Also, one note here is that I'm talking about temperature, but obviously this effect is visible in the polarization anisotropies of the CMB. But in this work, we focus on temperature, so that's why I'm focusing mostly on that during the talk. What's interesting about lensing is that it introduces new type of a new non-Gaussianity in the CMB, which we commonly call secondary, to distinguish it from the primordial non-Gaussianity that comes from inflation. And in fact, if you, if the CMB was totally Gaussian, then what you would have is that its odd endpoint correlation functions are 0, and the even point correlation functions are basically can be written in terms of the 2-point correlation functions of the power spectrum. However, in this case, as you can see, if you, for example, think about the 4-point correlation function of CMB anisotropies in time in the case of the lens CMB, then you have the unlensed temperature modes, but you also have other terms that add to the your 4-point correlation function and give you basically something that it's a connected form of it, basically. And this signal, this secondary non-Gaussianity, is very interesting because it can be used to reconstruct the lensing potential from the lens CMB maps. In the case of if we assume that the lensing potential is Gaussian, then we can say that the power spectrum describes its all statistics. And in particular, under this assumption, the power spectrum has been detected. And I'm just mentioning the, let's say, last detection, which was done by Planck in 2018. And this detection has been done to high statistical significance at 40 sigma. And in this plot taken from the paper, I'm just showing the power spectrum, so the power of this signal in terms of the scale, basically, here in the x-axis from different types of experiments. I mean, the fit is quite well. But most importantly, the power spectrum, so this signal has been used to also draw some constraints on cosmological parameters, and especially on parameters that are more related to late time cosmology. So not only the density of matter, omega n, but also sigma 8, which is the basically the amplitude of the linear matter power spectrum at 8 megaparsecs. And here you can see the posterior distribution on these two parameters. The red one is the basically taking the primary CMB anisotropies, so temperature and polarization from Planck, and the blue one is same contour but with lensing. And as you can see, it already has improved the constraints on both of these parameters. So my message here is that adding lensing to the primary CMB anisotropies is quite interesting because you get tighter constraints. At the same time, you can also get some information on this on late-time cosmology from the lensing potential itself. But again, this was done assuming that it was Gaussian. So what we do now is kind of go beyond this Gaussian assumption from the lensing potential. So let me see. Now, I don't want to create confusion. I'm talking about Gaussianity, non-Gaussianity in many observables. So there's one type of non-Gaussianity, which is the one induced by lensing on the CMB. But then there's also the lensing potential. And in this case, I'm talking about the non-Gaussianity of the lensing potential. So I hope this is clear. Well, in case you're also free to interrupt me for questions, I don't mind it. And what happens is that when you have, at late time, when you have nonlinear clustering of matter, this generates basically a non-zero matter bispectrum that in turn induces a non-zero bispectrum of phi. And so here we're focusing on that. This is important because it has been shown, in particular in this paper here from 2016, that the lensing bispectrum will be detectable with next generation CMB experiments. So assuming that this signal was subdominant, was negligible, was a good assumption for experiments like Planck. But for the sensitivities of next generation experiments, like for example, Simon's Observatory and CMB S4, this signal will be detectable and with a certain statistical significance, and it can be used to also constrain cosmological parameters. And here on the left, I'm showing the cumulative signal-to-noise ratio of the bispectrum, taken again from this paper, in terms of the maximum multiple that we can observe. And where you can see that for that here they consider three different types of experiments: stage 3, deep and wide, that have different specifics, but these are experiments that are, for example, ACT, Simon's array, or Simon's Observatory, and stage 4 like CMB S4. And you can notice that it's really impressive that already with stage 3, we could detect the lensing bispectrum, but it's specifically also with stage 4, the statistical significance increases quite a lot. And so it's something that definitely we should look at in the future. But another very important result of this paper that really caught our attention was the fact that if you assume that you measure the lensing bispectrum and you have your nice data, then combining this to the power spectrum improves the constraints on some cosmology, for example, the sum of neutrino masses and dark energy, by up to 35% with respect to using the power spectrum alone. And so adding the information of the bispectrum would definitely not only break some parameter degeneracies, but also improve our knowledge on neutrino masses and dark energy, hopefully. And so this makes the bispectrum an appealing observable for future experiments. And this is the reason why we wanted to look at it. But reconstructing lensing from CMB anisotropies is easier said than done. It has some challenges, and this was the focus of our work. Let me just give you a brief overview of how we reconstruct lensing. The lensing potential from the CMB anisotropies. This is usually like a very efficient and somewhat optimal way to do this is by using quadratic estimators. In particular, the one that I'm showing here in the flat sky approximation is the so-called Okamoto quadratic estimator, and it's called quadratic because it depends on two of the CMB anisotropies. Here again, the temperature. And this estimator has, as I said, the temperature anisotropies, but it also has a filter function and a normalization to make the estimator optimal and unbiased. So a filter function is chosen to be in a way that the estimator is optimal, and the normalization in such a way that the estimator is unbiased. Now, if you think about the bispectrum of the lensing potential, then you need to have 3 copies of phi. And so what you get here is a bunch of integrals and filter functions, normalizations. But more interesting, you get a 6-point correlation function of the temperature anisotropies. In the same way, if you think about the work done before for the power spectrum, you have 2 copies of phi. So here you have a 4-point correlation function. So there is an increase in complexity in these calculations. When you compute the 6-point correlation function in the orders of expanding in orders of phi, as I showed you in some previous slides, then what you obtain is you obtain the signal that you were looking for, so the bispectrum of the lensing potential, but you also obtain some additional terms that need to be removed that are called noise biases because they arise as a consequence of the quadratic estimator that you're using. And these biases depend on the lensing power spectrum, and here the nomenclature that we use really reflects this because we have 0 for the first noise bias, which doesn't depend on explicitly on the lensing power spectrum. It comes from the estimator itself. It's there because you're using the estimator basically. And then you have the N1 noise bias, which is a first order, so it's linear in the lensing power spectrum. Let me skip this and go to the N2, which is quadratic in the lensing power spectrum. And then N3 halves depends on the bispectrum, so it contains the signal itself. And so I'm already kind of spoiling you some results with this slide, but it's just to give you an idea of what is our problem. What we're looking at is 2 plots where I have plotted the bispectrum into different configurations, the equilateral one where the sides are the same, and the folded one where you have a folded triangle. And basically in gray and black, you have the signal, which it was modeled using 2 different fitting formulas that are cited here. And you see the basically the 2 largest noise biases here. And as you can see, especially at high L, so at in this part of the plot, the noise biases bury the signal. So the signal really is buried by these noises. And if we want to retrieve the signal, then we need to take account of this and carefully remove them. So this is the problem we're looking at. Any questions so far? Now, before I go into details of the paper in particular, I just wanted to give you a quick recap of what I talked about so far. So, as I said, going beyond the Gaussian assumption for the lensing potential is kind of the right time now, because we will have experiments that will be sensitive to the bispectrum. And this is an interesting signal because, especially if combined with the lensing power spectrum, can give us a very important information on lead time cosmology. And unfortunately, though, the signal is buried in reconstruction noise. And our goal is to quantify the magnitude of these reconstruction noise biases as say in a way in order to pave the way to the detection of the signal. So as I mentioned earlier, what we need to do is to compute a 6-point correlation function. So obviously a way to do this is to use the Wick theorem. So do this with the standard Wick expansion and contract the relevant and have the relevant contractions between the fields that we have at play here. But we also tried another way, which is a bit faster, which is using Feynman diagrams. And you might wonder, why do we use Feynman diagrams? I mean, we're not in particle physics, but it's just the idea behind it is the same. You have a certain function that describes your field, and you have your contractions, and we can use Feynman diagrams to get our results. And how do these diagrams look like? So they can have these features here, where you have here in this case you're basically depicting a 3 times 2-point correlation function, but they can be more complex, as I'm showing here, where you have, for example, a 4-point correlation function and a 2-point correlation function. But you can also have the connected 6-point function as in this diagram here. But don't worry, I will go into the details, in particular of the first diagram, because it's also the easier one to kind of give you an idea of how this works, and also how it can speed up calculations. So let's go to the basic rules. We start with a building block, which is this block here, with two vertices that correspond to your temperature anisotropies. And they have also their momenta assigned to that. And this building block corresponds to the filter function and to the normalization. Then we define propagators, that we have a straight line between two vertices that describes the, let's call it temperature interaction, even if it's not really that, but it gives you the temperature power spectrum. And then we have a wiggly line, which gives you the lensing potential power spectrum. Then at each vertex, there's momentum conservation. So this is a general rule that we use. So just considering these three very basic rules, we can start with our diagrams. We have bispectrum, so we have a 3-point function. Therefore, we need 3 building blocks, each with their vertices, and so you have 6 vertices that correspond to your 6-point correlation function. Then if we take the expansion that I showed you earlier and we take the lowest order possible, so we have basically unlensed temperature anisotropies. So we stop here in our expansion. Then what you have is just the straight lines, because this corresponds to the temperature, let's say temperature interaction. And then you use momentum conservation to each vertex to redefine some of these multiples, because they're not all independent. Indeed, they depend on only one small L. And then you can already, from this diagram, you can already write down your expression, which is an integral over this small L that basically the other ones are integrated out by the delta functions at each vertex. And so you have an integral over L1. Then you have your filter functions in terms of the multiples. Then you add 3 temperature power spectra corresponding to the 3 straight lines. And then you have a symmetry factor 8 that maybe is not evident right now, but that's the, let's say, the power behind these diagrams, is that it's very easy to see the symmetries of the problem. Well, usually you would have to compute all the permutations in the correlation functions. Here you can actually just see it from the diagrams, because it's very easy to show that in this expression here, if you exchange these straight lines inside the vertices, inside one building block, then the system is symmetric by that. And so what this means is that you have 8 different diagrams like this, with the straight lines combined in a different way, that can be reduced to just one of them. And so that's how you have the 8th factor here. And basically you're done. You got your first noise bias. So this is N0. It's true that it's very easy. You can compute this also with doing your more traditional way of Wick theorem. But in this way, we just had to draw a few diagrams, and then we got our expression immediately. One other nice feature that's very that makes this method very interesting is that you can see immediately from the diagrams where does actually, from which part of the connected of the 6-point function the diagram comes from. So for example, in this case, you can draw 3 different rectangulars that correspond, each of them correspond to a 2-point function. And indeed, N0 comes from that term. And you can see this because this is a connected part of the diagram, because if you cut through it, you will cut a propagator. While if you cut through here, you will not cut any propagator. And basically this defines connected part of the 6-point correlation function. You can go on with your expansion, so add more lensing potential, and this reflects on the diagram as well. So for example, if you go on in this function, then you will have a wiggly line, which is your lensing potential interaction. So you have lensing potential power spectrum here. And again, you can see the connected parts. So now you have this rectangular that corresponds to a connected 4-point function, because you cannot really go through this without cutting a propagator. And then you have in the upper part a 2-point correlation function. This type of diagram, but it's not the only one, corresponds to N1. But you can see that, like, if you had to do your calculations by hand, then you would have to compute a 4-point correlation function times a 2-point correlation function, all the permutations, and so on, adding complexity. But in this case, you just see it from the diagrams. And then you can move on with your expansion. And here you have a 6-point correlation function connected. And this diagram corresponds to something that contributes to N3/2. Indeed, the 3 wiggly lines here that meet at the center, they correspond to a bispectrum, a lensing bispectrum. And then you can go on with your expansion to higher orders of pi, and basically add more wiggly lines and more interactions. So once we have our FEYNMAN diagrams and everything, so we can actually go into some to compute these noise terms, and what we do is also validate them with simulations. So I'm just gonna go very quickly through the pipeline. In particular, here we focused on the largest noise biases. So we focused on N0 and N1 because they have the highest contribution, and also they're also quite easy to simulate as well. So it was something that we could also validate with simulations. So let's take N0. N0 is quite simple as a term because I showed you it really depends on just the temperature and isotropies. It doesn't have an explicit dependence on the lensing potential. And so what you can do here is take the CMB power spectrum, the lens CMB power spectrum, and draw a realization from it to build a map. You take your spherical harmonics coefficients, and then you use the quadratic estimator to reconstruct phi from it, and you use a bin bispectrum to compute the bispectrum from the map, so from the spherical harmonics coefficients of the map. We do this for, as I already mentioned at the beginning, for 2 types of triangle configurations. We consider the equilateral and the folded one because the signal is very interesting in these 2 configurations, and we leave out the squeezed one for different reasons that I will explain later, especially when I'll show the folded. So basically we draw a lot of realizations, a lot of simulations, and compute the bispectrum. However, when you have your bin bispectrum, it contains only N0, because, as I said, you're not really introducing any lensing in your map. You're just changing the variance of your map by the power spectrum, basically. So you just have a map with the different variants. And then you have a Gaussian realization, which means that you don't have any non-Gaussianity in it. So you only have N0. This is the result that we get compared to the analytical findings that I showed earlier. So you have that the blue line is the equilateral shape, and the match with simulation is quite good. And then we have the folded one, which is a negative noise bias. So that's why I put it in as the dash line. Where you can see that, especially at high L's, it matches quite well with simulations, but then there's some discrepancy that shows at lower L's. And we thought about this, what it could be, maybe due to simulations, but it's actually an effect that it's due to binning. As I mentioned here, we use the bin bispectrum because it's faster, simply because of that, because computing the bispectrum from the map requires a lot of time. And so we use the bin bispectrum, and depending on the size of the bin, unfortunately, the result changes. And this effect was already noticed in this paper from 2019 on the, not on noise biases, because they weren't looking at that, but on the lensing bispectrum itself. And it depends also on the configuration that you're using. As you can see, at least for N0, so for these scales, the equilateral shape is not affected by it, at least not visibly. And we see here that if you consider the folded slicing, if you change the number of bins that you're using, the result will change also dramatically. So what I showed you earlier is 60 bins. And you can already see that at 20 bins, your result is very different from your analytical expectations. And you can see it from the residuals as well. It's quite evident. Then when you increase the number of bins to 60, you mitigate this effect. But then going at 100, you already see an improvement even with respect to 60. And the reason behind this, there's not only one reason. Well, first of all, here we're looking at a very small type of signals. As you can see, this is the 10 to the minus 12 signal that you see here, magnitude. And the scatter that comes from each realization can be quite high. And so at these small signals, you can have also some negative values. Then if your bin is too large, then this gets averaged out. And so your average result will be biased by the bin size. This is one of the reasons that we consider. Then we move on to the N1, which is a bit more complicated to simulate because N1 depends explicitly on the lensing power spectrum. And so we cannot consider just a map with a lensed power spectrum, but we really need to have a realization of an unlensed CMB map here. And again, a Gaussian realization of lensing map, and then use the lensing map to lens the CMB map in order to obtain your lensed CMB map. And after this, you proceed in the same way. You reconstruct the quadratic estimator, your lensing potential, and you use the bin bispectrum to compute the bispectrum. And in this case, you have three different terms that arise from this computation. Again, here we are talking about Gaussian realization, so we don't have any bispectrum effect in it. So we have the N0 because it arises just because you're using the quadratic estimator. Then you have N1, which is the term that you want to validate, but you also have N2 because N2 depends quadratically on the lensing power spectrum, so it will arise if you have this type of lens map. However, we use a result from a paper from 2011 where you can mitigate the effect of N2. I will not go to the details, but you can do this if you reconstruct, so if you use the quadratic estimator in a non-perturbative way. And in this way, you can basically cancel some of these of the N2 terms contributions, while the contributions that are really low, they just don't, you can ignore them. So you basically mitigate the largest contributions from N2, which is what we need. So we can basically forget about this term, and then we have just basically N0 and N1. So now in order to get from your simulations N1, you need to subtract N0. There are different ways of doing this. One of them would be to get your analytical result and remove it basically. So subtract it to your simulation. However, in our case, this wasn't precise enough, especially at higher L's. And our guess is that it's because, again, we are looking at very small signals, and the effect of N0 is quite large with respect to it. And so we wanted to do something that would be more accurate. So what we do is remove the N0 of the map. So we do from our lens map, we reconstruct N0 as we did before, and then remove it. So intuitively, we're taking from our map, we're taking the N0 from that and removing it directly. So this is the intuitive idea behind it. This works quite well because we get quite a good match with our noise biases, especially in the folded shape. You see some mismatch again, which could be to binning, but this is a bit lower than expected because, and our intuition is that the fact that we're using simulated N0 probably mitigates this binning effect. But in the case of the equilateral shape, there are some oscillations here at IL that the simulations cannot capture. It's very difficult to capture them. This probably means that we need more simulations to have these features. Even if here we consider we consider 10,000 simulations, so it's quite a high number, but probably given this oscillatory nature of the curve, it might be that we need more. Nonetheless, the result is quite good because again, our data points correspond to the curve that we were expecting. So let me go to conclusions and future direction, because what we did so far was, was important to kind of open the door to the reconstruction of this signal. So CMB lensing is important because it allows us to constrain like time cosmology, and in particular, being able to detect the bispectrum with allow us to take a leap forward towards more precise constraints on cosmological parameters. But the signal is buried in reconstruction noise. And in this paper, we were able to model these terms theoretically and then test them with simulations. So we have a picture of what this reconstruction noise looks like, especially on the on the largest contributions that will bury the signal. But there's a lot of work ahead. For future work, we plan to include polarization data in the quadratic estimator, because this will reduce the noises. When you add more information from the CMB, it will reduce the noises. So we want to have the minimum variance estimator. Then we would like to, what we're working on actually is to perform a similar analysis on N3 halves, because this term contains the signal, so contains the bispectrum, so it needs to be taken account for very carefully, because it might bias a lot the bispectrum, especially at high L's, where we expect it to be more important. Then one crucial step is also performing realization-dependent analysis because this is more robust to systematics that come from instrumentation, and it's called realization-dependent because it mixes data and simulations to reconstruct the noise, to reconstruct the lensing potential. And finally, last step is, once we have built this pipeline, is to compute, so to detect the bispectrum with upcoming data. In our case, a goal would be Simon's Observatory, because we expect a detection with 5 sigma. And so it would be very interesting to do that. But obviously, we also look at other experiments, as for example, CMB S4, which might yield higher statistically significant detection. And thank you so much for your attention.
Thank you for the nice talk. Are there any questions from the audience? While people gather their thoughts, first I'll ask a question about, so you mentioned that the lensing, using the lensing bispectrum would improve the constraints on the cosmological parameters. You said like addition to power spectrum, improve like something like 30%. I was wondering if this improvements will come in a particular direction, breaking particular degeneracies, like what kind of, what exactly will lensing bispectrum add in terms of constraining the parameters? Is it just overall better contours or some particular directions?
I think it's it's overall better contours on the parameters, because it will add information to your analysis, basically, in this case. So that's our hope, is to as I mentioned from this very preliminary forecast in that paper, they see improvement of 35%, which is I would say quite good, especially on parameters, for example, as neutrino mass, because it really could help us kind of narrow down the neutrino mass hierarchy. And if you think about experiments that will have a higher resolution to that problem, then this adds up, and hopefully, we'll have a better understanding of that. But thanks for your question.
Right, thanks. One more question. You said lensing bispectrum will be detected in the future surveys, and if I understood correctly, the lensing bispectrum depends on the 3 L1, L2, L3. So when you say detection, would that be some like binned bispectrum in the L space, or each of those will be able to be detected?
Yeah, I think it's a binned. I would say, a binned bispectrum. I think, we will look at these configurations that I mentioned. Also, I forgot to add about the squeeze, because people think, oh, why don't you look at the squeeze? So unfortunately, the squeezed configuration has some, first of all, the folded one adds more, is the largest contribution to the signal to noise, and so that's why we also looked at that. But the squeeze is affected by this binning effect a lot, so it's very difficult to get good results from it. You really have to have a very sharp binning. So we decided to ignore it, at least for this work, because it would require a lot of time to get results with it that were significant, at least. But I would say we will look at the binned bispectrum, especially for these configurations, and measure that.
Right, I was maybe wondering if in the squeeze emit this lensing ISW bias, which causes the a significant CMB bispectrum, maybe affects a lot to your like the 6-point correlation function. But I'm not entirely sure there.
Yeah, it might be. So, well, in this, I want to go back, but no. Okay. Well, where is it? Yeah, in particular in this paper, they look into reasons why because they see this effect on the lensing bispectrum, and it's quite evident in the squeezed one. And so, looking into that, one of the reasons they give might be that the squeezed one captures a lot of non-linearities, and simply your theoretical modeling cannot capture all of that, because there's also one other challenge that we will for sure encounter in doing this, is that this depends on your matter bispectrum modeling. And so it really will depend on that, on how good we model the matter bispectrum.
Right, yeah. So if there are no other questions, shall we close the talk?
Oh, there's
Oh, sorry. Actually, sorry, I see a question from Ben.
Hi,
Hi,
sorry.
Benedict.
Hi, nice to see you. Well, I just had a question as someone who's using pseudo CLs. We never really care about the noise bias there, except for we have the constant shot noise. And I was always under the impression that quadratic estimators were the superior estimator compared to pseudo CLs. Do you think that we're missing something that more than what we're already missing by using pseudo CLs, or is the noise bias somehow very pronounced in quadratic estimators compared to other estimators?
Well, yeah, let's say that the noise biases are really characteristic of the quadratic estimator. And one question could be then why you're using quadratic estimators. It's just because, I mean, if we want to do these calculations in our lifetime, then we need to use something efficient. So there are other ways, but they're kind of slow, especially in view of the massive data sets that we'll receive. And so I think, like, yes, the noise biases are probably just characteristic of the quadratic estimator. And so I don't know if you're, I mean, I'm also not sure about your question, what it is in particular, if you're asking me if you should use quadratic estimators.
It was more because I'm not using quadratic estimators.
Okay.
But I'm also not measuring the bispectrum, I'm just measuring power spectra. But yeah, I always thought that quadratic estimators would solve several problems that we have with just using pseudo CLs.
Okay. Well, the good news about this problem, at least that we're facing here, is that it was the same of when they had to reconstruct the power spectrum, is that when you actually work with data, you use this method, which really, where you can remove your noise biases through simulations and data itself. So through this combination that I mentioned of data and simulations. And so this makes it easier. In this work, we just wanted to be sure that we know what we are looking at, so that once we use the realization dependent analysis to remove those biases from data, we know that we remove them.
Okay, thanks.
Thanks.
Any other questions? If not, let's close the talk here.